Let's see how we're doing with the concepts of continuity and limits. They're somewhat related, but different questions. So first we're doing some limits. The right-hand limit, as we approach 2, it looks like we're on this path on the graph. So we are getting as close as we wish to a limit of 3. Even though there's an open endpoint, we get right up to 3. And as we approach 2 from the left side, we are approaching a limit of 5. And here there's no plus or minus, so we're talking about the overall limit. Since our left-hand limit and our right-hand limit did not agree, the overall limit does not exist. How about as we're approaching 5 from the right-hand side? Well, we're on this path here next to the vertical asymptote, so we're headed to negative infinity. So I like to use that arrow instead of an equal sign to remind you that technically this is not a numerical answer. Infinity is a concept, but we do not ever really reach a limit. And on the left side of 5, we're in this section of the graph next to our asymptote, and it is going to positive infinity. Now, even if both sides of the graph were going to positive infinity or negative infinity, it is still, the overall limit would not exist at an infinite discontinuity. Okay, let me erase my marks on the graph here, and let's continue with discussion of continuity. All right, so we've got open endpoints here. Let's pay close attention to the question, is the graph continuous or discontinuous between -5 and -1? So from -5 to, let's try -1 way over here, and we can clearly see that we've crossed a vertical asymptote, so there's an infinite discontinuity. Very easy to rule out. How about the interval with an open endpoint at 2 but a closed endpoint at 4? Well, let's take a look. So open endpoint at 2, closed endpoint at 4, and we do have continuity right up to that open endpoint. So there's no problem. It would be discontinuous if we wanted a closed endpoint, but that open endpoint, and can we get right up to our closed endpoint? So I think that one works out fine because the parenthesis and the square bracket are in the correct order. So similar question, but very different location on our graph. How about open endpoint at 5 and a closed endpoint at 6? The closed endpoint at 6 doesn't bother me at all. We get right up to that limit. And remember, at a closed endpoint, you only need a one-sided limit. So we only need to get right up to that endpoint. This, I think, is a trick question because what happens on going over to 5? So do we ever reach a limit that you could answer? So because it's headed to negative infinity here, we couldn't really say a limit that we get to here. So I think that we're going to pick discontinuous. Frankly, I'm not sure that that question with an open endpoint next to a vertical asymptote would ever come up because different textbooks might handle that differently. But there is no numerical limit there at that endpoint. So I think that would fail the definition of continuity. Okay, how about the closed interval from 7 to 9? Again, let me remove some of my markings here. So the closed interval from 7 to 9, and let's take a look at the graph. You can see our problem there is right in the middle. There is a removable discontinuity. And how about open endpoint from 11 over to infinity? Well, I think we're looking at this section of the graph. And yes, there's an open endpoint there, but that's okay. We can get right to the endpoint even though it's not closed. So we have continuity here. Oh, I guess technically this is not typed the way I would think. So I'm not sure if that was meant to be part of the question. Remember that you can never actually get to infinity. So if this had been a parenthesis, then I think we could have said it's continuous. This very well might have been my typing error. With a closed endpoint on infinity, we would have to say it's discontinuous. because we cannot ever reach an endpoint at infinity and close it. All right, so there were a couple details there. Decide whether these functions are continuous at the given constant c. So is this natural log function continuous at the constant c? So let's let that x coordinate be 2. So what do we know about this function? It is our natural log function, 2 units to the left, so we know what the graph looks like. Has its vertical asymptote at x equals -2. Is it continuous when we put 2 into the function? So I think we can see that this point would be 2 natural log of 4, and I don't see any reason that it would not be continuous. The left-hand limit and the right-hand limit certainly match, so I would say yes. And if you were asked here again, technically you should say because the left-hand limit equals the right-hand limit. And we know what that limit is equal to. It is equal to the y-coordinate, the natural log of 4, when we put 2 into that function. So this would be your argument that yes, it is continuous. How about at pi over 2? Well, if we tried thinking about our limits here, the sine of pi over 2 is 1, but the cosine of pi over 2 is 0. So you can see that we're going to have a division by 0, so there's going to be a vertical asymptote there. So there's going to be an infinite discontinuity. An infinite discontinuity at x equals pi over 2. So no, obviously it is not continuous. And how about the greatest integer function? Might be worth reminding everyone, I think now you've seen this enough, this step function, that you'll remember that it is discontinuous at every integer it steps up. So it has jump discontinuities at every integer. So is it continuous at -3? Well, I guess I should go over here to -3. So we'd actually have this point that's running off the edge of my view here, of my screencast. Let's see. So this is our point here at -3. So this point would be at -3, -4. So it is continuous from the right side, but it is not continuous from the left side. So if you were going to explain, you'd say the limit as x approaches -3 from the left side would be -4, and the limit as x approaches -3 from the right side is -3. So there is a jump discontinuity. And in fact, we could say that greatest integer function is going to be continuous between every n right up to n plus 1. So we could say, this isn't part of this question, but if it's useful at some point, we could say the greatest integer function is continuous over every interval closed endpoint n to open endpoint n plus 1 for all integral values of n. Okay, so that answers the reverse of the question, not where is it discontinuous, but where is it continuous. All right, let's press on here. We've got first a polynomial function f, and then we use that polynomial function as the numerator in a piecewise defined function. So notice that this polynomial of 4 terms would be the numerator of this function. So our first question A says find all the zeros of f. Well, to find the zeros, we want to find out what makes the y-coordinate equal to 0. And a little reminder of factoring by grouping. Group the first 2 pairs. Group the second 2 terms. And now we have a GCF of x minus 3 and the remaining factor. And of course, I'm sure you guys would have factored that right away in one step. So we know that the zeros, f of x is equal to 0 at x equals plus and minus 2 and at 3. So now look at our piecewise defined function. In part B, it says find the value of p so that function h will be continuous. Well, let's first look at what the function really looks like now. So now we know a little bit about that numerator. We've got it in factored form. So now let's put in that numerator f of x in its factored form, and you'll see what we know about limits. I'll scroll here so I have a little space so you can see what this question was getting at. There's a removable discontinuity there. And when x is equal to 3, we have this unknown value of p. All right, so what do we know about this function? If we want it to be continuous, so it's a parabola. This, of course, is x squared minus 4. So it is parabolic everywhere except the x-coordinate of 3. So you already know how to graph this function. So the idea here is that it has a hole in the graph at this point. So how can we make sure that it's continuous as a piecewise function? We make sure that this value of p plugs the hole. So we say that often here. If we want it to be continuous, we do not want to keep this hole in the graph here. Well, I think you already know what that coordinate is going to be. If you put 3 into the parabola, 9 minus 4, you can see that that is going to be at 5. So what do we need here? We need p to be equal to 5 when x is equal to 3, and that would fill in the hole in the graph. Okay, so if p is equal to 5. So it's simply a matter of looking at your limits, your removable discontinuity, and then look at your remaining factors. All right, and then the question C, determine whether h is even, odd, or neither. Well, now that we've got it graphed, we know it's a parabola, and if p is 5, now we've filled in. So there's a mirror image on the other side here. So we see the symmetry to the y-axis. So we can answer that this is an even function. All right, let's proceed. Now we've got to do a little bit of algebraic work. We've got another piecewise function, and we want to find the value of c that will make it continuous. Well, we know that the first part of the domain here, I'll circle this part in blue, we know that this is going to be a polynomial. Better than that, it's quadratic, so we know this part would be a parabola, and parabolas certainly are continuous. And the other piece of the domain, let me work with that one in red so you can see where I am. We know that that's going to be a straight line. And we certainly know that lines are continuous. So we could say f is continuous everywhere except perhaps at our trouble spot, x equals 2. So what we really hope here is that the two pieces of the graph connect with each other. So for continuity, what we would need is for the left piece of the graph to join up with the right piece. So for continuity, we require our definition of continuity. We need the limit, the left-hand limit, as x approaches 2 from the small side, to be equal to the right-hand limit as x approaches 2 from the positive side. And of course that would still mean there could be a hole in the graph. So remember part 3 of our definition, the limit has to exist and the hole has to be filled in. So it has to also be equal to what we would get by direct substitution if we plugged in f of 2. Well, look at our domain here. when x is less than or equal to 2. So these two pieces of the graph, these two fit into the same domain. So we actually don't have to do that twice. So those two are the blue sections of the graph. And look at what the formula is, cx squared minus 3. And we would like that to be equal to the red piece of the graph, cx plus 2. So our question is saying, what value of c will make this work so that these two pieces pick up right where the other one left off? Well, this is the way that students often set this up, and then they don't know what to do because we've got the variable c and the variable x. But remember that we actually know that x is approaching 2. So this value of x, we actually know where we're working on x here. X can be replaced with 2. So in each of these, we know we're doing the limit as we get close to an x value of 2. And now our only variable that we're solving for is c. So we have 4c minus 3 is 2c plus 2. So 2c is 5. And we would want c to have a value of 5 halves. If c is replaced with 5 halves, then the left piece of the domain would pick up and connect with the right piece of the domain. All right, let's see. I think we got another one here that has 3 separate pieces. What values of a and b would make this continuous at x equals 3? Well, again, look at these are linear functions. 2 is a horizontal function. So we know that this is continuous. We know f is continuous everywhere except perhaps at the connecting point. Except perhaps at x equals 3. So for continuity, we need to use our definition of continuity. For continuity, here's what we require. We need the limit as x approaches 3 from the small side of f of x to be, and that part, by the way, in our piecewise defined function, whoops, I better read it the other way around. This is kind of written upside down. Smaller than 3 would be this piece of the graph. We need that to be equal to the right-hand limit as x approaches 3 of f of x. And that's when x is bigger than 3, so that's the red piece of the domain. And of course, we need that to be equal to f of c itself, f of 3. So f of 3 right here in the middle, and that's the easiest one, so let's fill that in first. We know that f of 3 is exactly equal to 2. So we can come up with, we've got this sort of 3-part equation. So this red comes from ax plus b in our piecewise defined function, and the left-hand limit comes from this green portion of our domain. And now notice, oops, I wrote x here. Let me point out here my mistake. I put x there again, but we know what x is equal to. X is going to 3. So we want to put a 3 in where the x is. Okay, so I caught that over here because now the 2b times x, we know that the x is going to 3. All right, so now I kind of made a mess there, so let's clean this up. This would be 6b minus a. And this piece would be 3a plus b. And of course, we can see that we want both of those to be equal to 2. So we've got really 3 different combinations here. So this is back to an Algebra 1 problem. So we want this first part to be equal to 2, and we want this second part to be equal to 2. So that might be the easiest thing to do here. So maybe you would solve this by substitution method. Solve for b, and then let's take this value and plug it into the other equation. So lots of different algebra steps here. So 12 minus I'm multiplying by 6 here. 18a minus a. So it looks like it's not going to be a pretty answer. So a turns out to be 10 over 19. And if we plug that back in there, b would be equal to 2. I'm going to rewrite 2 as 38/19 so you don't think this is too difficult. So b then would be equal to 8/19. So I think generally we get, we're used to math problems being written so we get integers, but that's not always the case. So once we get our limits, once we used our definition of continuity, so remember this is our 3-part definition of continuity. So once you do this a few times, that will be fairly simple to set up. All right, and let's see what we can do here. This is a little bit shorter to answer. So we've got a graph of our piecewise function. It's a parabola up to 1. And then it's another parabola between 1 and 3. And then it is equal to 4 from that point on. I think this maybe, this graph to me looks like that lines up at 2 more than it does at 1. So you might feel more comfortable if we change those and said it changes at 2 and 4, so I think that graph isn't labeled very accurately. So that correction might seem to make this match the graph a little bit better. Perhaps the graph slid over in your paper. Maybe it looked more like the original. All right, so we want to find a number b, so that f of x is continuous from -infinity up to the closed endpoint of b, but not continuous from -infinity to b plus 1. So, for example, I can see here that we can go right up to 2. So we could let b, for example, be something like 1.9. So here's what I'm saying. Is it continuous from -infinity to 1.9, but discontinuous from -infinity to 2.9? Can you see that we could pick any values as long as we crossed over a discontinuity between those 2 points? All right, so regardless of how your graph looks, maybe your paper, the graph is labeled at 1. But you've got the idea here that you're looking for an interval where there's a discontinuity between these two values. All right, question B says find values of a and b so that it is continuous on the closed. It's continuous on the interval from closed endpoint A to open endpoint B, but not with a closed endpoint. So our a value is the same in both. So we need it to be continuous right up to an open endpoint. So if I could use either piece of the graph. Let me focus on this part. So for example, I could say that it goes from, and again, depending on how you're reading your graph, 2 up to 4. It is continuous. But if I closed that endpoint, then it would be discontinuous. It does not have a closed endpoint, so it is not continuous on that right-hand side. All right, and C, find the least number a such that f of x is continuous from a to infinity. Well, I guess we're looking at this horizontal section of the graph. So I think that we could start at 4 and go all the way to infinity. So I think that is the smallest value we could pick. And that should do it.